Okay, so where were we? Just to remind you, this is the structure of the syllabus that we're talking about. We just talked about atom optics and just effectively and the interaction of a two-level system with a classical light field by taking center of mass motion into account. Now, the main result of the previous lecture is written here on this whiteboard, where we have an operator describing a pi pulse, where you reflect both the excited state or transfer the excited state to the ground state, get a negative momentum kick in interface, and the inverse process, and the operator that generates a superposition. So the excited state is with a probability of 1/2 and remains untouched. But from the excited state, you may also decay into the ground state with a probability of 1/2 and transfer negative momentum. The same is true for the ground state. The ground state also remains with a probability of 1/2 untouched, and you may transfer, excite the atom, and get a momentum kick. And those were the operators that we derived. Now, what we also, there's something weird showing. Okay, now, this is the plot that I showed you before with this odd time evolution. This here is the position. This is the cloud of atom, just taking a picture of the position. And we saw taking these pictures time after time, interacting with such a pi-half beam splitter, we now see that 50% of the atoms move apart. Then we have this mirror pulse that basically gives to the excited state a kick so that they go straight, negative momentum kick, and here positive momentum kick so that they move up. And then we need a final beam splitter to mix those two arms to get rid of which path information, if you like. And then you observe interferences back there. This is, of course, experiments are nice, but in theory, it looks a little bit cleaner. And this is now what we are talking about. We ended the last lecture with basically showing that a beam splitter looks like this in a space-time diagram. And we can draw an atom interferometer like that. Now, what we're going to do now is build a whole interferometer. So we have now the first beam splitter followed by a time evolution. And because time evolution, you always have to write them as operators, you always have to multiply them from the left. And that's why the time axis is going to the left, because pi-half beam splitter, time evolution of the whole thing, mirror time evolution of the whole thing. And because I want to allow for some flexibility, I have here a different period of time so that the time spacing is not correct. And then in the very end, just another beam splitter. And that's the operator sequence that we are now going to calculate. And what are we going to see? We're going to see that we can describe the time evolution actually as a superposition U1 plus U2 with, let's say, square root of 2, which is a superposition of a time evolution along the upper path. That's U1. And U1, just talking about the external degrees of freedom, is some phase, phi 1. And then the time evolution of the atom with momentum p, and the time evolution of the atom with momentum p plus h bar k. So we first have increased, so external motion. So we first have increased momentum, and then we have just decreased momentum again. Whereas the propagation along the lower arm is just U2, e to the I phi 2, also a global phase. And it is exactly the other way around, external P plus H bar K, so increased kinetic energy, and then U external of P. And that's what we are going to see today, that we actually can write this as such a superposition. And we see actually what makes up the phase of an atom interferometer and the contrast of an atom interferometer. What we're not going to do is show that it's susceptible to gravity, and we are actually how the loss of contrast emerges, because that's what we start with tomorrow. And by that, I think we can again move to our second chapter. So this is episode 2, and we talk about the structures of atom interferometers. Yes.
You have like any consideration of coherence laser versus the first one that opened the
Very good question. Yes, because I sneaked in an superscript up here which says L, and L is the number of the pulse. When you look at my slide here, I also have now a superscript pulse 0, pulse 1, and pulse 2. And I have here laser phases as well. This is phase phi L. That's the laser initial phase of pulse L. And if these phases are not coherent anymore, they will fluctuate. And you will observe that actually you will erase the signal if the laser is not coherent. So yes, indeed, you need a coherent laser that interacts 3 times. And that's something we're going to see. Okay, good. So let's just now talk. So we understood what's happening during the pulses. Let's now talk about the time evolution between pulses. Between pulses. And I guess I'm gonna zoom in. Okay, so the Hamiltonian is now again, oh, I don't know what happened here. So the Hamiltonian is now, because we have no interaction, actually, we can treat the internal and the external degrees of freedom separately. So we can now write H as nothing happens to the external degrees of freedom times the internal Hamiltonian plus the external Hamiltonian, and I specified that anyways because that's p squared over 2m plus m mul g, whatever potential you like, times the identity of this internal Hamiltonian. And they act on the joint Hilbert space H is equal to H external times H internal. Exactly. And, you know, they decouple. So both degrees of freedom. Yes. The identity. So the point is, so you have now a system that has 2 degrees of freedom, center of mass motion and the internal motion. And you need a Hamiltonian that always acts on both degrees of freedom. So what happens if that my overall energy depends on nothing happens to the external? I can also write it. I just write down the identity. Oh, I'm not sure if you can read it. So for example, for the external degrees of freedom, that is something like EE plus GG. Okay, nothing happens to the internal states. The identity for the internal states, to the sorry, yeah, now I mixed it up. Internal states, and this is for the external ones. And let's go, for example, to position representation. That would be dz, z, using the completeness relation. Okay, just one representation in particular bases. Yes.
Why it separates the external and the internal degrees of freedom clearly, like if either internal degrees change it and external degrees stay the same?
No, I'm just talking. We have this is between the pulses, so there's no light on. Oh. The atom in the excited state will remain in the excited state and move, and that's it. And then the ground state, it will stay in this ground state and be subject to any potential. Okay, good. So we can effectively get rid of that. And now what you observe is that both contributions commute with each other because, you know, the Hamilton, so it's always identity and everything commutes with identity. So both parts commute with each other, and that's important. Let's just talk about the time evolution operator. And I used it a little bit this morning, but I will come back to that. So this is like a time evolution operator. So how is that defined? And I define it as an operator, unitary operator U of t. And that effectively just evolves an initial state by acting. So it acts on the initial state and gives rise to the final state. So that's what it's doing. We can also just use the Schrödinger equation. Yeah, and so it is 1 over h bar ddt psi of t. And I just take the time derivative of u. So that means I have I h bar du dt, because the initial state is time independent. Of course, the initial state is time independent. And I know that this is equal to the Hamiltonian times psi of t. This is just the Schrödinger equation. And so I can write this also as h times the unitary time evolution operator, always suppressing all time dependencies, times psi naught. And so we find that the time evolution operator is solution to the operator differential equation d dt u is equal to h times u. Okay, you might have known that. I just wanted to show it again because that's what we are talking about effectively for the whole interferometer sequence. That's what we are interested in. Now, because I don't want to calculate the interferometer in any representation or so, I just want to calculate the whole time evolution in this operator form. And so if the Hamiltonian is time independent, so we can straightforward solve it. And that's just taking the operator exponential. And that's effectively what we could do also for these Rabi oscillations that we observed. So we say u of t is equal to e to the minus I over h bar h of t times t. Or to write it in a little bit more fancy way, operator exponential minus I over h bar, the integral from 0 to t dt prime times h. And that's it. Now, of course, you have to be very careful because for arbitrary, you have to just be careful. You just find, we are not discussing this right now, but it is the time ordering operator times this exponential, where Hamiltonians with, well, a lot of times I evaluated to the left. Now I have to get it right. Is minus I over h bar integral 0 to t dt prime h of t prime. Okay, and this is time ordering. And this morning we've made our life easy and simple because we just worked on with time independent stuff, and we will continue to do so. Okay, so now I said both parts of this Hamiltonian commute with each other, and that's cool because when we remember our favorite Baker-Campbell-Hausdorff, we know that e to the a plus b is equal to e to the a times e to the b times e to the minus the commutator a b times higher orders, but we can neglect those. What that implies is effectively, because the Hamiltonian has this structure and commutes with itself, we can just write this separately. So we can now write this time evolution just as e to the minus I over h bar h times t. That's what we are discussing. And we can just write this as e to the minus I over h bar times h external times t times e to the minus I over h bar times h internal times t. And I'm going to just call this u external of t times u internal of t. So we can just separate and evolve the internal state and the external degree of freedom separately. Okay, why do we want that and why do we need that? Well, we are now going to calculate the internal dynamics. It's going to be trivial. I'm still allowed to say that, but tell me afterwards if it was okay to say that. And we will not specify the external Hamiltonian because we want to discuss different cases. Free atoms, atoms in a linear gravitational field. Alex is going to talk about rotations, and that's all encoded in the center of mass motion in this external degree of freedom. Now, the internal dynamics are easy. Again, a word that's forbidden, but having diagonal matrices is pretty cool and makes everything easy. So let's just think about this internal dynamics. We have H internal, and that is H bar omega excited times the excited state, the projector, plus H bar omega ground times the ground state. And now taking the exponential, U internal of that is the exponential of minus I omega e times t times the projector minus I omega g times t times the projector. And now, of course, you can also say, oh, actually they commute and projectors are idempotent, so it's a diagonal matrix. So having the matrix exponential of a diagonal matrix is just having the entries on the diagonal being exponentiated. And that's what we are doing right now. So in fact, what we observe is that this here amounts to e to the minus I omega e times t plus e to the minus I omega g times t projector g. Okay? So now we have a projector and the excited states oscillate with omega e and the ground state oscillates with omega g, as you might have seen already when people were talking about Ramsey interferometers, about Ramsey clocks, about atomic clocks, because that's what you measure when you have clocks. Okay, so let's now talk about this Macht-Zehnder interferometer. So what I just introduced on that slide was a beam splitter, mirror, beam splitter. That's like a Macht-Zehnder interferometer, and that's what we're, of course, everything can be generalized to arbitrary pulses, but let's just stick with that. Total Macht-Zehnder sequence. So how does that now look like? Well, my time evolution now can be stitched together, and that is an exact description, of course, except within our approximations, which is, but so we have now this pi half pulse as pulse 2, a unitary time evolution between those pulses, and this is for a time capital T plus delta t. Then we have a mirror pulse, index 1 or superscript 1. We have a time evolution for some time t, and we have s pi half 0. And just for the sake of mine. So, okay, in principle, we could also include time evolution afterwards, but this is common to both arms. It would drop out. You can ask me about that later, but it's not important. Okay, so now the point is, when we now look at the space-time diagram that we had before, having here the ground state and here the ground state, and this would be the ground state, and the excited state, we see that we have two exit ports at the end of our interferometer. One is defined by atoms in the ground state, and the other one that drifts away, the blue thing, is defined by atoms in the excited state. And what we're interested in for now is just in atoms in the ground state that leave the atom interferometer. And we will see later that they take a special form. And this is exactly the form that I gave back there. So what is interested as well, we just assume all atoms come in the ground state, they are not excited. We apply our pulses, and we detect all atoms in the ground state as well. So what's relevant is the matrix elements. Yes?
I don't understand the schematic here. What is...
Oh, I'm sorry. I didn't say this is position and this is time. Do you understand it now?
Put the beam splitters.
And I put in the beam splitters. Yeah, I put in the beam splitters.
Okay. Yeah.
This is the mirror. And so this is pi over 2. This is pi. And this is pi over 2. This is exactly what we had before. In space and time, it looks like that. So now let's talk about the matrix elements. And so I will demonstrate to you that this matrix element is just G, or the matrix element G, U tot times G takes the form of 1/2 e to the I phi global, a global phase. We won't be interested in that. And then a superposition of U1 plus U2. And because we looked at the matrix element of our internal degrees of freedom, you know, having brass and cats G acting on our operators, this operator only acts on the center of mass motion. Acting on H external. So we still have the external degrees of freedom, the motion of the atom included in this operator. And we will see, so first of all, we will see that they are unitary. So we will see that Uj is the description along one arm J or branch J. And we will see that those are now unitary as well. Which implies that Uj dagger times Uj is equal to the identity of the external degrees of freedom. Okay. Now, I said, okay, that's what I'm going to demonstrate. Before I show you that this actually is a superposition, let's just assume it for a second it is. And what I'm now going to demonstrate to you, first of all, what do we detect? And why is this matrix element relevant? And thirdly, oh yeah, what's contrast and what's the phase of an atom interferometer? So, I know, maybe they are all...
Thank you.
Yes.
Could you repeat what the label of pi of the
GL, global. It's a global phase. It's not, it will drop out later on. Any other questions so far? Yes.
Where are the S matrices? Like, they disappear, right?
They disappear. And that's because we, in some sense, not traced out, but we projected on the internal states. I will show that later. Yes.
So you've written that the time could be different, the time space
Yes.
could be different between the two pulses. So then would you have an energy difference from spending more time in the excited state or the
And I wouldn't call it energy difference, but a phase difference.
Yeah.
Yes, because that's exactly what a clock does. A clock is in two different internal states for a different amount of time. And that's a clock phase that you can read off. There is another effect, and we will see later tomorrow, that if the atoms spend different amounts of time in different internal states and momentum states, the wave packets don't overlap anymore. And we will see that that will lead to a loss of contrast.
This picture, it looks like they spend the same time.
Yes, because I just drew something.
But for that matrix element, does that not include that
It-
difference?
The phase difference, I will show you how we will observe that phase difference. The phase difference is included in this U. Okay?
I have one
Yes.
question. So on the left-hand side, you have a matrix element.
Yes.
On the right, still an operator.
Yes. Because I took a matrix element between the internal degree of freedom and the U total acts on both degrees of freedom, so also the center of mass motion. And that's why it says here still acting on the center of mass motion.
That's the key thing. Because when you look on the left-hand side, you would think, oh, that's a number now. But it's not, because he still hasn't taken expectation with respect to the center of mass motion.
Exactly. And
The operators on the right-hand side are only center of mass motion.
And we need to specify actually the initial state. And actually, if you have an open interferometer, unequal time spent there, the overlap depends on the width of the wave packet and so on. And actually, in that case, initial conditions enter your signal. And that's bad for an atom interferometer, because as soon as initial conditions enter and initial conditions fluctuate, you get an additional uncertainty in your signal. So for high precision measurements, that's bad. And that's why you usually try to, have everything perfectly overlapping, because you don't like initial conditions entering the phase. Okay, so let's talk about detection. And I showed to you those nice figures taken, or absorption images taken by the Quantus experiment. And effectively, what did they do? They took a photo of all atoms in the ground state. This is just a photo. What does that mean? How would I write this as an operator? So it is an absorption image. And that's the following projection operator. It is projecting on Z and G. That means I'm looking at the position Z. That just gives me the position. And the ground state G. So this tells me I have that probability of having an atom at position Z in ground state G. Now, that's basically just taking the photo. Now, to evaluate that, also in an optical interferometer, you can look at the spatial structure of fringes and whatnot. Or you say, okay, I have two exit ports. I'm just interested in all the light that comes out in one direction of my beam splitter. So what we are looking at for now, Alex will generalize that, and Jason also. We will now look at all the atoms that enter the atom interferometer in ground state G. How do we do that? We basically sum up this position distribution. So we get the position, we just integrate over all positions, and by that we get the number of particles in the ground state. And that can be seen by the completeness relation that Dorte just asked, because we now, exactly, so now we have the integrated particle number, where we just say, okay, good, pi projector on atoms in ground state G is just integrating over all atoms at one particular position. And having that in the ground state, completeness relation, this is just the identity on the external degree of freedom times G. So that tells you I have my cloud, and I just take basically all the pixels, assign atom numbers to them, sum them up. And then only for G, because that, exactly, we measured only for G. Okay, so now we have to somehow think about an initial input state. So let's think about an input state. We now assume, of course, that those atoms are non-interacting. Otherwise, my Schrödinger stuff wouldn't work. So let's say our input state here, psi in, and I make a capital psi, is equal to psi naught times G. So G is just an atom in the ground state. So the atoms that enter are in the ground state. And psi naught is just some center of mass motion, just some wave packet. Yeah. You could also go in with excited state. You even could go in with a superposition, but then it might already be susceptible to phase differences. Yes. So this here would be now the center of mass motion, a wave function. Center of mass wave function. Okay. So the atoms, all atoms are in the ground state and have some momentum position distribution. And now let's calculate the ground state population after the interferometer. And the ground state population, I just call it IG, is just the expectation value. I don't need that. The expectation value of one external times G. So this is just the number of atoms in my ground state. And that's the interference signal in the ground state. And we now take our initial state and we take our time evolution, because this is now with respect to the time evolved state. So what I have to do, I have to take the initial state, and the initial state is G times psi naught. I just interchanged them, please, because it's getting easier if I do it that way, times U total. That's the time evolved state. I take the state, evolve it in time through the interferometer. Now I have my projector. So and of course, I have to do that from the left as well when taking the expectations value. So this is psi naught, and this is G. And of course, I have U total dagger because I just multiplied from the left. Okay, and now I have my projector, and I just leave out. What's this? Okay. Mozilla did something. In my projector, I also leave out the external motion. And that's actually what we have to calculate. I project now on this. And now you actually observe what we have right now, because we have now at this point here, we have at this point this matrix element that I was talking about. Yes, please.
When you do your body cycling and when you do your imaging, you need to have two different excited state hyperfine level.
Yes, because you have to excite or something like that. Yes, but I didn't really describe that. I just assumed an operator that projects on the ground state, assuming that the signal is always linked to the atoms in the ground state. Okay, and just also, this here is this operator thing that we just talked about, but we also observe that this guy here is just G times U total times G dagger. Okay, nothing happened. It's just a trivial thing. Okay, and now let's assume the form of this as I mentioned before. So we said before, okay, if G times U total times G is equal to 1/2 e to the I phi global, you're going to see now why this global phase is nothing that worries me. And we have U1 plus U2. We can now calculate this matrix element. This is the form, and I just plug it in for our interference signal that we saw above. And that's IG is equal to 1/2 times 1/2, that's 1/4. I have this global phase, but it's the global phase times its complex conjugate, so that drops out. Yes. Yeah, because the operator on the left, so this is still an operator because I just projected on the ground state. But the operator, in fact, acts on both the internal and the external degrees of freedom. So there's still an operator acting on the external degree of freedom. Okay, so it's still an operator, but just acting on the center of mass motion. And so what we observe is only, and now that's the point, here is the expectation value with respect to the center initial wave function, center of mass wave function that survives. And I just have now U1 dagger plus U2 dagger times U1 plus U2 times psi naught. And now that's very easy to calculate because those operators are unitary. We can write this as 1/4, and U1 dagger times U1 gives rise to 1. Taking the expectation value is just 1. The same is true for U2 dagger times U2. So these two, this here acting on this guy and this here acting on this guy, both of them just give rise to an overall factor of 2. Plus, now we have this guy acting on this guy. No, sorry. This guy acting on this guy and this guy acting on this guy. They are not, they are different operators. So what we observe here, in fact, is the expectation value of psi naught times U2 dagger times U1 times psi naught plus its complex conjugate. It's just a C number right now because we're talking about an observable. And what we're going to do is we're just going to call this here the overlap operator. Because it describes the overlap of the wave function that propagated along one arm with the wave function that propagated along the other arm. And that's the overlap. And if we can calculate that overlap operator, we're done. So we have here the expectation value, or this expectation value gives propagated wave packets that overlap in the very end. And in principle, this is a C, so the overall interference signal is, of course, not a C number, but this expectation value is 1. So this expectation value of the overlap operator is what is of interest to us. So this is psi naught times U2 dagger times U1 times psi naught. And this can be a complex number. And we write it as modulus and phase. And this modulus is just an ugly V. And a phase e to the I phi. And of course, this is element complex number. Modulus. And this is the phase. And now if I plug that into my interference signal, what we observe is actually Ig is equal to 1/2 1 plus this modulus times cosine phi. If I plot this now as a function of phi, so this is phi, and this is Ig, it's something that oscillates around 1/2. Here's 1. And what we observe actually is that we have here for V equal 1, that it oscillates between 1 and 0. And for having V smaller than 1, we observe something like that. So what we see now is we have to calculate the expectation value of this operator, of this overlap operator. And we look at its modulus, and that gives us the visibility of our interference fringe. And we look at its phase, and that gives us the phase of the interferometer. And that's all we have to do. Yes? No, I already canceled it with the 1/4. Yeah, I didn't say it, but I did do it. Okay. But of course, what we haven't taken into account is, yes. Yes. In U2 and U1 only act on the external state. This is only the center of mass motion. And they will take this nice form. Oh, I will play a trick with the propagation phase of the internal states. You will see later. Yeah.
I don't know if this is, but what does the modulus describe now?
It is the visibility of your signal, the contrast.
Oh.
The modulus of this operator is the contrast of your signal. Or visibility, I'm always bad, but this here is something that I will call now, let's say, visibility. So in principle, there is no background and so on. Everything is up to some degree idealized, but yeah, not that badly idealized. Okay, are you all with me so far? So this is what we have to calculate. And this is what we are going to do tomorrow. We are going to calculate the modulus and the phase for having gravity, having no gravity. And well, effectively, that's what we're doing tomorrow. And then Alex will show you what happens if you have quadratic potentials, if you have rotations, how they will affect at least the phase. But what we will see is, why do we get a loss of contrast if we have, for example, quadratic potentials and not perfectly overlapping wave packets? Because the wave packets don't overlap. So effectively, the modulus of this expectation value is not identity anymore. Okay. Good, but what I didn't do is now, basically I just said, okay, believe me, and never trust anybody who says believe me. But I will demonstrate to you that actually it's true. The only assumption that we made is we can divide up our propagation into two arms, U1 and U2, and everything is hidden in U1 and U2. And now we have to somehow, at one point we have to do the work and actually calculate what U1 and U2 looks like. Yes?
Phi is the thing that happens along the arms, or?
No, that is, phi is the phase of the overlap. And that's something that you have to calculate. That's the phase of your interferometer. The phase difference. So think about wave packets doing stuff. They can get very ugly. Going up here can get very ugly. They come back to the same place. You just overlap them, and then you get a global phase difference between the two. You get a spatial dependent phase difference between the two. You have to integrate over that. That will lead to a loss of visibility and so on, because they're displaced.
But this is not a spatial.
No, because we integrated over all spaces, so it's an effective phase that comes back that.
Phi really tells us how the two went into different things, no?
And so
usually we have when you have lasers and then one of them goes through a glass and then gets a phase.
Yeah, so the question is, so exactly. So that's effectively what we want to measure is included in that phase. And if we have gravity, we will see tomorrow, we have gravity, phi will be minus kgt squared plus delta phi. And this is coming from the laser pulses, for example. Okay? And this is kgt squared. And g is what we want to measure. That's gravitational acceleration. Okay, good. So I'm not sure if I made here. Yeah, okay. So we don't have subchapters. I forgot about those. But now let's calculate the evolution along these interferometer branches. So we have to calculate the matrix element now, because that's what I said. Okay, believe me, the matrix element takes that form. Now I'm going to demonstrate to you it takes that form. And for that, we now need the specific form of our pi/2 pulses. So far, we have specified them, but now we will rely on their specific form. So now we are going to have G times U total times G. And that is now, if we remember, G times S pi/2 of pulse 2 times U t plus delta t times S pi of pulse 1 times U of t times S pi/2 of pulse 0 acting on G. Okay, that's what we have to calculate. And in fact, if you have a different pulse sequence, you could make a pi/2 pi/2 pulse or anything like that. You just have to modify it, but it's not a big deal once you understand the principle. Okay, so let's just recall our beam splitter pulse. It's right at the whiteboard, but I just write it down again. SL pi/2. How is that? And maybe I just move this a little bit down. So that is 1/√2 external times the identity of the, let's say, excited state minus I e to the I phi L plus kz times the transition element going from ground to excited state minus I times e to the minus I phi L plus kz times going from the excited to the ground state plus the identity times the projector on the ground state. Okay, so this is what we are having. I will talk about the other thing later, about the mirror pulse. So let's just now talk about, let's just talk about this contribution here. And this will be contribution 1. So this little calculation, what happens? You come in with the ground state. So nothing happens on the top left. But of course, this ground state will act on the ground state. And this ground state will act on the ground state. That's effectively what we calculated so far. So we know that S0 pi/2 on the ground state is equal to 1/√2 times identity external times G minus I times e to the I phi naught plus k times z and the excited state. Okay? Good. What's the next step? Well, the next step would be looking at this guy here, because this is effectively the same thing. This is contribution 2. So this would be the ground state acting from the left on our beam splitter. And this is beam splitter 2. And now what happens? Well, if we multiply from the left with the ground state, only this guy here acts, and only this guy acts to the left. So these are the only 2 contributions. And we can write this as 1/√2 times 1 external. So it's still an operator acting on the external degree of freedom, as you see. And now it's G acting from the left, minus I times e to the minus I phi 2 plus kz times the excited state. Okay, good. So now we are halfway done, even though it doesn't look like it, but it's faster than you think. Well, now we have to multiply, we have to calculate this contribution here. What do we need for that? We need the time evolution. And the time evolution is something that we just, that we just needed. So it is u of t is equal to u external of t, and I don't specify that yet. And now I have the internal degree of freedom, and that's coming back to your question. E to the minus I omega excited t, projector on the excited state, plus e to the minus I omega ground state t, projector on the ground state. Okay? So we now, for this third contribution, just have to take this red guy and multiply from the left with this time evolution. And what do we observe? So contribution 3 is just u of t times s pi over 2, 0, acting on the ground state. What happens? Well, we just find 1 over root 2. And now we see in the ground state, projecting on the ground state, we just see e to the minus I omega ground state times t times the external degree of freedom evolved for a capital time t times g minus I e to the minus I omega excited t times u external of t times, exactly. And now we have this difference here. It is e to the I phi naught plus kz times excited state. Okay? Yes. No, I've not, this is still, I'm sorry, yes, I should be more precise. This is just the operator, or still the operator, because we have just having it acting on the ground state so far. Okay? So that is now the contribution with this matrix. And yeah, I'm sorry, we once have to go through multiplying matrices. Now the fourth contribution is doing the same thing from the left. So effectively calculating this here. Okay. How do we do that? So it is 4, contribution 4, and that is g. This is s pi over 2 pulse 2 times u of t plus delta t. And we find 1 over square root of 2. And we now just have to multiply this orange or yellow contribution from the left with our time evolution. And what we observe is now the time evolution e to the minus I omega in the ground state times, I'm sorry, here should be capital T, of course. I just copied it, but it's of course capital T. And this is the clock phases. This is what you observe in a Ramsey clock. Capital T plus delta T. This is the timing asymmetry. And then you have U external of T plus delta T. And then again, the ground state from the left. Minus I e to the minus I omega excited times T plus delta T. So this is the time evolution in the excited state. Still times U total, external times T plus delta T. And now I messed up because we have to, when you look at this, you know, we are multiplying from the right So here I have first to introduce the displacement operator, the momentum transfer. So I have first e to the I minus I phi 2 plus k times z. And now I have u external of t plus delta t. And then I have the, from the left, the excited state. Okay? So this is just multiplying, I'm sorry, from the right now, this operator. And we see here the order is different, and that will tell us something later on. And finally, what's left is the pi pulse. So when we're looking at that, we now calculated everything here on the left of the pi pulse and everything on the right of the pi pulse. So the only thing is that we have to still to sandwich the pi pulse. Let's remember what the pi pulse is. As pi of pulse 1 is equal to minus I times e to the I phi 1 plus kz times the transition from the ground to the excited state plus e to the minus I phi 1 plus kz times, sorry, of course, going from the ground state to the excited state and the inverse process. Okay, is there a question? Is there a question? I know, yeah, in principle, this also would be a great homework overnight to just multiply matrices.
What's that homework?
And an early lunch.
These are not want to have homework. Finally,
Some reaction.
Please, tomorrow I took names and pictures. Everybody has to be by tomorrow morning. Definitely not.
Okay. So when we now take the sandwich, what do we do? So let's just go through it. Let's just say, okay, we take this contribution here from the right, all of this. We have to multiply it with this contribution here because this goes from the excited state to the ground state. And then for the final part of the evolution, we're in the ground state. That's this. So that's the only part that's remaining. So I find, okay, I just write G times U total because that's what we're calculating, times G is equal to, first of all, I have 1 over square root of 2 times 1 over square root of 2. That's a factor of 1/2. And then what you observe is that you have minus I times minus I. There is just this minus I in front of both contributions. So what we observe is minus I squared. That's this type of global phase that I was mentioning. And then we have U1 plus U2. And now I just demonstrated to you what U1 is. U1 is the following. I just have to go from the top to the bottom. U1 is starting with e to the I phi naught plus kz. Then I have the time evolution in the of the external degree of freedom. Then I get some phase in the excited state. Then the second contribution is now this pi beam splitter. Here, this contribution here. Oh, it erased it. Okay. And that's just reducing the momentum. So this is e to the minus I phi 1 plus k times z. Okay. And now I'm looking at this contribution here, just the external degrees of freedom. And I find that I have U external times t plus delta t and a phase e to the minus I omega g times t plus delta t. Nothing happens in the very end. Okay? So let's go through that also. Okay, let's I think because I need enough space for that, let's just do the other arm as well. I start with this guy here. So this would be U2. And this is just the external time evolution for a time t. And evolution in the ground state for a time t. Okay? Nothing happens at the first pulse. There is no momentum transfer. Then I have this contribution here, G and G. So this would be now here at this point, e to the I, phi 1 plus k times z. So I give it a momentum kick next. Then again, I have this time evolution here, which is now u external times t plus delta t times e to the minus I omega excited times t plus delta t. And I have on the very left something that I first forgot, and that is e to the minus I phi 2 plus k times z operator. And now I have two operator sequences. And now let's try to interpret those. And for that, of course, we just make another drawing. And now we make this space-time diagram again, and we just make the space-time diagram very large. So this would be the position. And this here is the time. And now you see why this operator ordering is important, because we come in here with the ground state. And now there is a first pulse. Here is the mirror pulse. And here's the third pulse. And now what do we calculate? We come in with the atom. And now the green part describes first a momentum kick, then a free time evolution. So we're moving up. So that should be green, actually. We're moving up here. Okay. Then we reduce the momentum again. So e to the minus ikz, we just go straight. And then at the final beam splitter, nothing happens. We go straight. For the blue operator, nothing happens at the first pulse. There's no momentum transfer, so we go straight. At the mirror pulse, we transfer momentum, so we go up. And then at the final, we reduce the momentum again, so we end up in the same exit port going straight. So from going from having really a time evolution with different internal degrees of freedom and so on, we now think in terms of different arms or different branches. And we have now described the center of mass motion along those two blue and green branches. And that's exactly the first figure that I showed to you today. Okay, so that means just rewriting now everything. There is a lot of stuff there, but we have two arms now, and we can separate everything in two arms. And we have now arm 1, or branch 1. And that is U1. That is U1. And what do we observe? Now I collect all the different phases and just the phases and talk about the operators later. And this is e to the minus I. And we have now omega excited times t plus omega ground state times t plus delta t. Okay? Plus omega phi 1. So the phase of laser pulse 1 minus phi naught, the phase of laser pulse naught. That's the laser phase. And then we have the external motion for a time t plus delta t. We have a momentum transfer, negative momentum transfer, kz, and we have u external for time t and e to the I k times z. Okay, and that's so great that you have been at least asking questions during my first lecture quite a bit. And one of those questions was, I don't know who asked that question. So actually, why do we calculate this type of sandwich? E to the ikz, some function, depending on a momentum operator, times e to the minus ikz. Because it appears here. And what did we learn this morning? Well, this morning, so first of all, I don't want to write this all of this stuff up here. So let's just call this phi 1 because, yeah, it's just a phase. So we have e to the minus I phi 1. And what we observe now is we have the external motion for t plus delta t. And this is acting on the center of mass motion. It depends on the Hamiltonian. And it depends by that on momentum, and it depends on position. So we just write it as a function of hat z and p. And now we have this function that depends on z and p, and we sandwich it between this momentum displacement operators. And that means we just have the external motion of t and z and p plus h bar k. So for the first part, the upper arm is moving with an momentum, increased momentum. And during the second period, the upper arm is moving with, again, the decreased momentum. Obvious, you know, it doesn't look surprising and nobody falls off the chair except for almost sleeping, but not because of surprise. Now, the same is true for branch 2. Yeah, and then we are almost done. So U2 is now e to the minus I. And now I'm collecting again omega g times t plus omega e times t plus delta t. So effectively, the arms of those two, the roles of the excited and ground state are just interchanged. This is the type of clock phases. And then we have a phase that rises minus phi 2 that, yeah, and I excluded this minus, so that's here. So it's minus plus phi 2 at that point, minus phi 1, because this phi 1 has the opposite phase here on the lower arm, because the momentum is transferred in the opposite direction. Okay, and now we have in the very end a reduction of momentum e to the minus I kz. If you just remember this picture here, that's the blue thing. We get a momentum kick in the very end to end up in that particular exit port. We have u external that depends on time t plus delta t. We have e to the ikz, and we have u of t. Okay? And so, of course, this operator ordering actually is important, and the sequence of it. So we can also just define this as phi 2. And we, again, use the sandwich rule, and we have e to the minus I phi 2 times u external of t plus delta t and z and p plus h bar k. So for the second period of our interferometer, the momentum has been increased times u external times t and z and p. And that's what I promised you at the beginning of this lecture here. Okay, and now what we're actually interested in is in this overlap operator. Are there any questions so far?
Range 2, we get the difference between phi 2 and phi 1.
Yes. Yes, because if I scroll up, because here phi 2 is associated with a negative momentum transfer, and that's acting here on this blue arm, redirecting it. And phi 1 is now increasing the momentum and imprinting a positive phase. And that's important. Usually when you also look at Rabi oscillations, usually these phases actually describe the direction on the blosphere where you do the Rabi oscillation. And now I explicitly included it into my operators because I have multiple pulses and we will play with those as well. Chirping will come in again as kind of like the overarching tone of my lectures. Any other questions? No. Okay. So let's now look at the overlap operator. And now I just suppress the dependence on the position just because it's not important, or because there is no position increase. Let's put it this way. So it would be now U2 dagger times U1. This is what we want to calculate, or its expectation value. And it is e to the I phi 2 minus phi 1 times U external dagger of T and P times U external dagger of T plus delta T and P plus H bar K. Okay, this is now taking the dagger implies that we have to reverse the order of those two. And that's effectively a backward propagation in time, if you like. And then we now have to just write down U1, and that would be U external T plus delta T and P times U external times T plus P plus comma P plus H bar K. And now this is the sequence that we have to calculate. If you want, you can think about it. Time evolution with increased momentum, time evolution without increased momentum, backward time evolution with increased momentum, backward time evolution without increased momentum. That's it. And that's what we're going to do tomorrow morning. Yeah, I guess morning. We will calculate that for delta T equal to 0, delta T not equal to 0, free atoms without gravity, atoms with gravity. And we will look at its modulus of this expectation value. We will observe that under certain circumstances, it will be just 1, the modulus. And we will observe a phase. And this phase will include information of our laser pulses. And that's, you know, this phi 2 and phi 1 and so on. They include the laser phases. And if the lasers are not stabilized, you have to average over that. And that means that if you don't have a coherent light field all the time, you will just average out your interference signal because the laser phase explicitly enters. And on top of that, we will see that gravity acts on it. Okay? Any questions? No. Oh, daughter. Just because I'm lazy. Yeah. Yes. Yeah, so that's of course what I neglected. So in principle, we could also use all of this, and then it's getting actually difficult. A little bit more difficult. Yes, in principle, you would have to use those trigonometric function cosine, sine, and so on. If they are just pure cosine functions, you could calculate that, and you would observe also contributions that arise from a finite pulse duration. No, they will give rise primarily to a phase contribution. However, and you can also just sit next to Sam during dinner and ask that question again, because he just wrote a paper on that as well. But also what the problem is for finite pulse duration, these beam splitter matrices are not perfect, because also I have to take this velocity selection into account. And that gives rise to momentum operators. And then all the magic that I did here is not that easy. So you have to think about ways to incorporate that. But in principle, it can be incorporated, for example, with methods that Sam is developing. On top of that, there's also, we calculated these matrices in one particular interaction picture. Now, here, the time evolution is given in a different picture. There is no difference between the two if I just assume infinite pulse durations, just delta pulses. Now, if they have a finite duration, they will also give rise to finite phase contributions, and you have to take them into account. You have to be a little bit more careful. Other questions?
That's for level.
Yes. If you take Bragg, you can do the very same thing, but you have to work with projectors on specific momentum intervals instead of having excited and ground states. It's getting a little bit more messy, but effectively it comes up to the very same thing. You can write it down with momentum projectors and momentum intervals that define your two levels. Yes. So yeah, exactly. And we will see that tomorrow. Okay, we will see that tomorrow. Okay, finally, I just don't want to send you off to dinner without showing that there is some truth behind what I've been telling you. So episode 2, structure of atom interferometers. This is what we now calculated. And this is now a typical interference signal. And what I like about this figure is actually yeah, exactly, sorry. So, okay, so what do we observe here? Actually, this is an experiment where they effectively tilted the setup. So effectively, they changed gravity. They scanned gravity, but this is just to scan the phase. So think in terms of this axis as the phase. And on this axis, this is the population in your ground state. And what you observe is oscillations. But what are those dots? Those dots are now so you perform the measurement and you observe one outcome. And you have one specific number. And we basically mark this percentage of this atom number in one exit port with a gray dot, transparent dot. And so we were performing this for a couple of times. I don't know how often they did that. But basically overlaying gray dots, it gets more darker. So what you actually observe here is the distribution of the number of atoms in one particular part averaged over many, many runs. You see the distribution, but I was just saying, okay, I'm just interested in the first moment in the expectation value. We just have the expectation value fitted to a cosine, and we observe this here. We observe also that the signal doesn't go from 1 to 0, but just from 0.9 to whatever. So we observe that there is a loss of contrast. And that is due to this imperfect overlap, for example. What we also observe is if we just look at this marginals, just summing up, making statistics, for each population that we observe, we observe a distribution like that where we can extract contrast, just the contrast and the amplitude of the signal. This is the interferometer that we had. That is an experiment. This is what we calculated. We used these operators down here. And this is actually written down in a nicer way what we did today. We observe here now this momentum transfer, time evolution, momentum transfer in the opposite direction, and so on. And we have now here this compressed value. And with this, I'm also 5 minutes early, so it's up for questions. Anyways, I guess we can also put these slides up. But there are a few hands, so maybe back there, please. Yes.
Can you go back to the plot again that you just showed, like the yes.
This one.
What's the difference between these two?
Yeah, now I didn't explain that. I will explain that maybe tomorrow. I mentioned to you that you can do Bragg diffraction. So this is actually a Bragg experiment. You can do higher order Bragg diffraction. Just to remember, we have here momentum, we have here energy, and this is the energy momentum parabola. And you transfer momentum once. This is off resonant, and you transfer it twice, and this is resonant again. So effectively, you're scaling up the momentum transfer. And that's what's been done between 1, 2, and 3 effectively. What you observe is now that you transferred twice the momentum. That didn't work perfectly, and that's why you observe a lot of contrast. And what you also observe, that your phase scales and increases by a factor of 2. So your fringe period increases by a factor of 2. We will learn tomorrow that the sensitivity actually depends on the number of transferred momenta. And you see here that effectively, because there is because the fringe period increased, the slope also at this position here, for example, increases as well. So this is just to show to you that we can scale up the momentum, we get an increased fringe visibility, and we get an enhanced sensitivity because of that. And we will talk about that tomorrow. And the third one is not a second order Bragg experiment, but a sequential Bragg experiment. Or it was the other way around, I forgot, where effectively we first transfer momentum and then transfer subsequently again momentum. This is one of those large momentum transfer techniques that are being routinely used. And it also increases the fringe periodicity. Okay? Further questions? Yes?
Yes. In the previous picture, the one with the experimental one, previous one, this one, kind of looks like there's some part of the beam leaking through the mirror pulses, no?
Yes, there is a part. And that's also what I showed to you before. This is velocity selectivity. And because these atoms are not addressed by the mirror pulse, they just go straight. They don't end up in our exit port, but in fact, and now you say, okay, now you're actually bullshitting me, because you said that you beam splitter operators are unitary operators, and they are. But of course, if I lose atoms, I have to think whether this is still a unitary, so atom number preserving evolution. And at that point, it gets a little bit more difficult, as some of us know. But in principle, you can also think about routines, how to incorporate those.
Sorry, what do you do then?
Well, you effectively have to write down an effective operator for this guy here, and then do the same thing here. But you can always, and that's the cool part, you can effectively distinguish the atoms that run here from those atoms up here by just looking at the photo at a different spot. So you can basically get rid of those spurious arms by just looking at a specific spot in space. Then you still have atom losses. But that's just decreasing the overall atom number. That's usually not that bad. However, it's actually one of the major parts of research in atom interferometries is thinking about, you know, of course, this experiment was done in 2013. If you're going to large momentum transfer, so you're having a lot of mirror pulses, and all the time you're losing atoms, that's bad. And if you want to build a gravitational wave detectors, people calculate with 10 to the 4 momentum transfers. And even if your efficiency is 99%, it's not that good. If you 99% times 10 to the power of 4 is still very low. So this is actually one major part of research, trying to reduce that spurious stuff that actually annoys you and deteriorates your signal. Yes. So, excuse me, I didn't understand the question.
No, it was on. Not the very first I minus P1.
Yes. No, because I mean that's something that we can easily do. Let's say delta. So what we will see is that capital phi 2 minus capital phi 1 actually will come up with phi 2 minus 2 times phi 1 plus phi 0. And now if you think about this, this is the laser phase or the initial phase at each pulse. So it is something like a discrete second derivative of the laser phase. And that comes back to chirping. If we now say that the laser phase of pulse L is something like phi 0 minus omega times t of pulse L plus k alpha times TL squared over 2, and that is something we will do, we will see that actually this type of chirping comes into the interferometer phase. And if you calculate that, what you observe, so this here for delta t equal to 0, we will see that it just comes out to k alpha t squared. Okay, and if we see that, that's pretty cool because our interferometer phase in a gravimeter is minus kgt squared. And so we have kgt squared and k alpha t squared. So if they are perfectly the same, we are always at the 0 fringe. And that's something that we're going to learn about tomorrow, because we can now lock our chirping to gravity and use this as a readout. Okay, further questions?
Basically, all you do as an input is changing those phi's, no, from the lasers. You're changing the lasers. Everything else is
Yes.
the same.
Yes. For a very perfect gravimeter, that's okay. Of course, there is adjustment in the very beginning, yes. But that's what you're doing. You also might change capital T, so the duration of your interferometer. Yeah?
The inputs,
yeah, ideally, exactly. So the point is the input stays, you want them to be ideally always the same. Because if you have spurious phase contributions, and we will see tomorrow how initial conditions enter, under which circumstances initial conditions enter. And if, of course, if the initial conditions vary, that's a problem because you have a phase fluctuation from shot to shot. And what we will see is as soon as the wave packets don't overlap perfectly anymore, initial conditions enter. So you always want your wave packets to overlap perfectly in both space and in momentum, in phase space. That you're also going to learn about tomorrow morning. So you want them to overlap perfectly in phase space, and in that case, you don't have initial conditions entering. And there are some compensation techniques. So for example, gravity gradients means that there is an harmonic potential on top of the linear potential. That means that the upper arm is accelerated in a different way than the lower arm. So they don't overlap perfectly anymore in the very end. So gravity gradients are a problem. But there are ways to compensate for that by adjusting the momentum transfer in the second pulse. The same is also true for rotations. Think about Earth rotation. Everything is rotating, and by that, effectively, your wave vector is changing in time. So your momentum transfer differs, and the wave packets don't overlap perfectly. And you can counterbalance that by effectively, for example, having a mirror on top in like a Bragg or Raman setup, where you just tilt the mirror to counterbalance that. And that is pretty much to just avoid initial conditions entering the setup and to increase contrast by having the wave packets overlap as good as you can do it. And that's basically the experimental adjustment that is being done in those compensation techniques. I guess everybody's getting hungry. Wolf, if you want to say a few final words for the day, and
That was day number 1. Thanks for keeping through. Noticed very few of you have closed off. Those who have, there's very good coffee shops out there. Don't do that again. One comment of a lunch. So I would like to establish a rule for them. I've seen some people are sitting with people whom they know. Don't. That's strictly forbidden. If I catch you again, I take away your food, no food today. Okay? So the rule is, if you have worked with that person ever in your life before, a minimum distance of 2 meters. Okay? The point is you're here to meet new people, not to talk to people. You can do that at your own time. That's what Zoom is there for. So try to meet people. After this, we have the poster session in the evening. There will be also some refreshments. There will be some nice things to drink. But there will also be posters. So have a look at the website. List of the posters. They're broken down into 3 sessions. So make sure that you put up your poster well before the start of the session. And the poster session is, if you go through here, on the left and the back. It's a lovely space with it's a nice space where we can all have a good look at your posters. We are planning, the speakers do not know that yet, so that's the news to you. You're part of the committee to select a few posters for poster prize. So do a good job, try to